why this opportunity is relevant. We'll touch on what exactly are virtual power plants, why they're useful, why they're needed, how hospitals can participate in a virtual power plant, the benefits that are on offer, and we'll discuss how this program or this participation provides a new benchmark for best practice generator testing. Rakesh will talk to some of the key considerations for hospitals in particular in terms of technical configuration and enrolments in a virtual power plant, and then we'll roll through a few questions towards the end, a bit of a Q&A session. So, grid challenges. There's no doubt everyone would have copped a good earful of what's been happening in the energy market or the energy world and our decrepit grid over the last few years. Yeah, our grid's certainly feeling the pressure. Just to touch on a few of these, heat waves threatening national power grids, power prices set to rise, bushfires threatening transmission infrastructure. There's been no shortage of press covering what's been happening in our grid, and our grid is a very unique. I mean, we're one of the first movers in the world in this sort of rapid transition to renewable power. So we're a bit of a litmus test with some other other countries. So it's a very exciting time to be in the energy world. So a couple of key themes with what's happening in the grid. So coal-fired power stations are retiring. This is taking a big chunk of supply or generation out of the grid. And during those critical heat wave days, during the summer, where there's high demand, and we're removing this supply, which has to happen as we transition to renewables. Supply-demand balance is getting tighter. So it means that on those hot days, demand increases. There's a risk of the market operator having to put areas of the grid into blackout to maintain a safe operating level. These same power stations are aging, and they're unexpectedly failing right where we don't want them to. Particularly during a heat wave when it's derated, and grid infrastructure is requiring maintenance to keep it up to scratch. There was an article which just touched on about the Loy Yang A power station in Latrobe Valley that was out for about 8 months last year. Taking a large number of megawatts out of the grid, and issues like the number of transmission interconnectors between the states. So the states can import or export power depending on what their requirement is. For example, there's a Basslink transmission interconnector between Tasmania and Victoria. When that's out, or that has been out on a few occasions for maintenance, and that causes a reduction in supply, which further exacerbates this situation. Of course, fossil fuels are being replaced by clean but variable renewable power. So when the wind isn't blowing and the sun isn't shining, the market operator needs these additional sources of capacity or flexibility or firming resources to help fill in those gaps and maintain that supply-demand balance. And of course, climatic events such as bushfires, heat waves, storms are threatening grid reliability. And we're starting to see a confluence of these events occurring at the same time. Coal-fired power station might be out for maintenance, a heat wave might roll through combined with a bushfire, and then a transmission interconnector goes down, and then the grid is absolute shambles. Wholesale power prices will go through the roof. Areas might have to be put into blackout. So we're seeing certainly a number of challenges to the grid. Run through this very quickly, but basically the chart on the left shows the projected closures of coal-fired power stations out to 2040. We're looking at about a 63% rate of closure of coal-fired power to 2040. And that's going to be replaced by this variable renewable capacity. And as a result, the market operator needs some dispatchable firming resources to help manage this, this variable renewable capacity as the grid transforms. So a couple of quotes here just to talk to the relevance of the opportunity. This is from the Australian Energy Market Operator. Targeted actions must be taken now to provide additional dispatchable capacity to reduce the risk of supply interruptions during peak summer periods. That's from their Statement of Opportunities 2019. And more recently from their Integrated System Plan. Expect on average 12 gigawatts, which to bring that to healthcare terms is equivalent to about 4,000 large hospitals. 12 gig of new dispatchable resources are required to back up renewables in the form of utility scale pumped hydro, fast responding gas-fired generation, of course, battery storage, but also demand response and virtual power plants are a key focus of the market operator to help manage this transition. So just before we jump into what are virtual power plants, I mean, I'll just say that this grid transformation is really presenting a risk to power security and reliability. But at the same time, it's providing this really unique, innovative opportunity for customers with flexibility, such as hospitals and backup generators, to participate and help manage this transition to a clean grid in the least cost way. Rakesh?
Thanks very much, Stu. So we'll get into what virtual power plants are, and I mean, you've obviously heard this phrase already, and I'll kind of help to give you a little bit of a primer. So a virtual power plant, by definition, if we could go on to the next slide, please, is a collection of assets across a large geographical area whose combined impact is equivalent to that of a single large power station. So you guys will have probably heard of demand response before. This is, a new way of defining demand response. And you may have kind of heard that demand response means turning things off. That's not necessarily the case. We prefer to use the phrase power flexibility, and that relates to energy users who have the ability to reduce or completely stop importing power from the grid whenever they want to. And there are a number of different assets that can provide the capability of doing this. And looking at that little list of pictures there, I'm sure you all see things that look familiar, except for maybe the kiln. At a hospital, you will see a generator, you'll see UPS, you'll see chillers, a number of fans, pumps, and maybe some of you even have batteries. All of these assets provide, are what's referred to as either discretionary, which means that you can stop using them without a major impact to your operation, or they provide you with full flexibility in that you can start using them instead of grid power, and then you don't have to import grid power anymore. And that has a positive impact to the grid. You can work together with assets like these to provide what we call critical grid response when the grid is stressed. This is a very cost-effective way for the grid to relieve constraints. That means when supply has increased and has reached a maximum, but demand is continuing to increase as well, there's nothing really more that can be done on the supply side, but the two have to stay balanced. So the market operator will call upon virtual power plants to provide their capacity, which means that customers make use of their flexibility to relieve the grid constraints. This is a far more cost-effective way of doing it than building a brand new power station. And what that means is that you reduce overall consumer energy costs because we place downward pressure on wholesale price by doing something like this. And ultimately, high wholesale prices are paid for by everyone, which I'm sure will be no surprise to those of you that have been comparing your energy bills from the last few months to the bills you may have paid in the equivalent months, 10 years ago. This provides a critical grid balancing service to the market operator as well, even when there are sudden reductions in supply due to power stations tripping or transmission lines dropping out. Within a matter of seconds, depending on the type of capability that customers have, they are able to make use of their flexibility and therefore help to balance the grid. With an increased kind of penetration of renewables into our generation profile, the intermittent nature is starting to show the need for more of this flexibility. So, for example, you could have solar and wind going great guns at any one time, and suddenly climate conditions could change such that the amount of power they're pumping out reduces, and that leads to a sudden need for flexibility. And the two of them can coexist to increase the penetration of renewables into the grid, which I'm sure we can all agree will be a good thing. So moving on to how hospitals participate in a typical virtual power plant event. So I'll talk through the panels that you can see on the right-hand side there. But in a nutshell, what we look to do with any customer, but especially a hospital that have critical infrastructure, is we will make use of the existing load transfer sequences that are already out there, rather than trying to reinvent a new one that may lead to issues in the future. So let's say you have a generator there, you have a UPS, and for the sake of argument, let's say you have one generator, one main switchboard. The top panel there shows you that before the event, you are receiving power from the grid. And then that middle panel there shows you what happens when a notification is received to switch over to generator power. This particular site here has a make before break configuration, or seamless switching. Closed transition is another way of describing it, which means that momentarily grid power and generator power are operating in parallel. Once the generator is fully ramped up and taken over site load, the main breaker opens, and now the generator is powering the whole site. This is a fairly standard closed transition switching arrangement, which I'm sure most of you are familiar with. And this is what we would look to make use of as part of a virtual power plant event. In terms of how it happens, there's a device that we would install on site, that yellow box there that you can see the little Wi-Fi label on. You don't have to make use of your internal IP networks. It's all done through 4G. But the device detects the need for a VPP resource to be used, and then sends a signal to your existing transfer switches to transfer over to generator. You transfer to backup power for the duration of the event. And then at the end of the event, if you decide to do so, you can switch back to generator. So what I should say there, I guess, is that let's say the event lasts 2 hours. You receive a notification, you run on generator power, but your generator stops working, or your generator doesn't start up successfully. That's absolutely fine. In a best case scenario, it will work and you run on generator power. It gets to the end of the event and the event has ended. We tell you that the event has ended, and typically you would be able to switch back to grid power. But if you choose to run on generator for a bit longer, that's absolutely fine as well. There's a lot of flexibility on our side and on your side as well. Ultimately, you are in full control. In terms of how many times you should expect this to happen, we're looking at typically about 30 hours per year of runtime, which is nothing, right? It's less than 1%, less than 0.5% of the total year. And you are paid for being available throughout the year. If there is scheduled downtime, or as I said, for whatever reason, your generator doesn't work, or whatever flexible assets that you're providing are not available, you can opt out at any time as well. All you have to do is just let us know, and then let us know again when the assets are available, and you will be opted back in. So if we move on, another example of how this can be done in a hospital setting. So as we said, the response typically imitates the hospital's existing emergency load transfer sequence. You can see in that chart there on the left-hand side, it's what we call the activate window. So the white line there is your baseline. It's how much power you've been using, and it's an average across the last few days. And the purple line is your actual consumption as measured using devices on site. You receive a notification to respond, and you can see that purple line starting to drop there because you are switching over to backup power. But in this particular case, the site is not switching fully to backup power. It's just a partial switch over. So during the event, that second section, the response section, the site is participating. And they've dropped into their reduction target, which is that yellow box. The white line shows how much they would have been consuming from the grid if they hadn't responded to the event. And then the difference between the white line and the purple line throughout the event is the magnitude of the response that the site has provided as part of the virtual power plant. And then at the end of the event, we have what we call the restore, which is where we say, okay, now the event has ended. If you choose to do so, you can switch back to grid power. In this particular case, the site has chosen to switch back to grid power, and you can see that purple line starting to climb in line with how much they would have been consuming if they hadn't been running on grid power, which is consistent with the last few days. And to give you an example of a hospital that did this, on the 31st of January 2020, it feels like a very long time ago given where we are in the world now, but it was a pretty tough time for the grid and for the country as a whole. You can see there on the top of the chart that green line denotes the total grid demand, and it starts from sort of 10 a.m. working all the way through to 11 p.m. on the x-axis. So you can see that green line starting to sort of climb slowly. There's a bit of a dip around 2:30, but then it starts to climb again. And that climb started to become a bit too difficult for the grid operator to handle. And they called upon our virtual power plant at about 4 p.m. So there was an activation window of about half an hour in this particular case. And you can see this site here, the purple box and the purple dotted line shows the demand profile of the site in question. It's about an 800 kilowatt consuming hospital. At about 4 o'clock, the activation began, and they switched their full site over to generator power. That pink sort of semi-rectangle shows you the event window. And throughout the event window, they were not consuming any power from the grid, so they switched over completely. The purple dotted line shows you how much they would have been consuming had they not switched over to backup generation. And then at the end of the event, which is around sort of 8 o'clock, so it's quite a long event, 3.5 hours. Our events typically have a maximum duration of 4 hours, but this was a pretty bad day and we nearly reached that maximum. The signal was received to switch over to grid power again because the event had ended, and the site chose to do so. So this was a day in which many bad things happened across the country. You know, we had bushfires, we had storms, all of these things sort of, as Stu said earlier, there was a confluence of all of these events taking place at the same time, which led to the virtual power plant being called upon, and this hospital was able to provide that critical resource. So moving on, we refer to these reserves as critical peaking reserves, and they are required when power supply is very short relative to demand. Now, shortages typically occur in a country like Australia. You know, the times when the grid is under the most stress. If we were to have asked all of you at the beginning of this chat when you expected them to happen, you would probably have got it right. It typically occurs on very hot summer afternoons and on evenings when demand is extremely high. In pure economic terms, it's standard supply versus demand, right? So third bullet point down, we use the price of electricity to track the grid need and trigger VPP activation, because as price starts to climb past the points that we consider to be the average, we can see that a bad situation is developing in the grid, in that supply is starting to reach a maximum and demand is continuing to climb. Price is typically around $80 to $100 per megawatt hour on average, but it can go lower, as we have seen in some parts of the country over the last few months, but it can also spike. The market cap is $15,000 per megawatt hour, and we have seen several instances of this cap being reached during critical periods. In 2019 as a whole, the total cost of power for the entire year was very heavily driven by what happened during this small number, this handful of critical peaking periods. So nearly 10% of all of the cost of power across the entire calendar year occurred during a handful of events, probably I would say between 30 and 40 hours across the whole year. And to give you an example of a hospital that has been participating with us for quite a long time, we have Ballarat Health Services that have been providing critical peaking resources for 12 years. It's a fairly simple and straightforward way of responding for them, in that when an event is called, they switch over to backup generation. It's what we refer to as the supply shortfall in the grid. And they run on generator power for the duration of the event. And then at the end of the event, they switch back to grid power, but if they want to, they can continue running on generator. They also participate in our frequency response program, which I'll tell you a bit more about on the next slide. So what is frequency response? So we previously have spoken about these events that are a little bit easier to predict, and it's a fairly straightforward supply and demand. But the unexpected imbalances in supply and demand can also come about due to some of the characteristics of the grid and the currents that are traveling through it. So some of you will know that the eastern seaboard of Australia has one electricity grid that is interconnected from the south of Tasmania all the way to the north of Queensland. We refer to that as the NEM. It's the National Electricity Market. That NEM has a high voltage grid operating with an alternating current at a frequency of 50 hertz, and the normal operating frequency band is between 49.85 and 50.15 hertz. It seems quite specific, but the reason that I brought that up is to show you that even the slightest deviation, within 2 decimal places, can cause a significant impact on power quality. So we provide, Enel's virtual power plants provide frequency response resources to the grid. In the event of a large power station tripping or a transmission line dropping out, hundreds of megawatts worth of capacity that were once there has suddenly disappeared, and grid frequency will drop off a cliff. So you can think of it as this sort of seesaw effect that you can see at the bottom there. Suddenly demand is outstripping supply because supply has suddenly reduced. So the way in which you can help to address this is to reduce demand and flatten out that bar, and Enel's virtual power plant provides that service. These events last up to 10 minutes because some of the larger power stations that are waiting on standby to support the grid longer term, whilst the power station that just tripped is being repaired, they take about 10 minutes to start up. The maximum event duration, as I say, is 10 minutes, but on average, we've seen that events typically last somewhere between 4 and 5 minutes on average. So if if we show you a case study of a hospital that has provided this type of resource, Echuca Regional Health, with our good friend Mark, who gave us that kind introduction at the beginning, they've been participating in our frequency response program now since around the October period last year. We installed a meter at their site, which measures grid frequency locally, and then detects the drops and automatically switches the site over to backup generation in order to balance the supply shortfall, helping to stabilize the grid frequency at 50 hertz. We obviously get paid for doing that. But the intangible impact from a market standpoint to the site itself, a positive impact, is that they have quite a lot of sensitive electronic equipment, and power quality is a very important feature in making sure that this electronic equipment continues to operate well and doesn't get damaged. So as you all probably know, deviations in frequency, are kind of a precursor to a power quality issue that may be catastrophic to some types of equipment. And participating in this program gives them the benefit of being able to run on generator and not expose that equipment to poor power quality from the grid. So moving on to emergency grid support. So this is a little bit more straightforward for most people to understand because it's been going for quite a long time in terms of a concept as far as demand response goes. Straightforward supply and demand events are fairly easy to predict. And as I've already said, over the summer just gone, we had a fair number of these events. So this is where, an aggregated portfolio of... It's a bloody fun meeting as well, if you don't mind my saying. So emergency grid support, you have an aggregated portfolio of sites, and, hospitals can obviously form a part of this aggregated portfolio that together respond and provide that virtual power plant impact, even though they're in many different geographical locations. These grid emergencies can be due to anything like extreme weather or unexpected system issues, or suddenly, for whatever reason, grid demand is much higher than the market operator had forecast, or a large power station fails unexpectedly. Basically, we need to have supply and demand within striking distance of each other, ideally with supply outstripping demand wherever possible. So if this is an issue that is going to come about, then the market operator does need to call upon demand-side resources to reduce their grid import and help to redress that balance. And again, we go back to the 31st of January 2020. I showed you that chart earlier on with one hospital providing that impact. There were actually several hospitals that provided their positive impact to the grid. Due to the extreme heat wave conditions, started off quite early in the day, started to get very, very hot. And then the bushfires were raging at the time. There were also some storms and very strong winds, which damaged transmission lines, which meant that even though there was theoretically enough generation, there was nothing to carry it to the destinations that it was supposed to go to. The network infrastructure failed as a result, and the amount of supply that was supposed to be available reduced. AEMO, the Australian Energy Market Operator, called upon virtual power plants across New South Wales, Victoria, and South Australia to reduce demand to prevent rolling blackouts. And within our portfolio, 97 sites participated, including 14 hospitals. We cannot understate the importance of the action that they took that day, because obviously it had a great community benefit, and it helped to keep the lights on for a lot of people who would otherwise have been finding it quite difficult. Back to you, Stu.
Okay, thanks, Rakesh, and apologies to everyone for that little technical mishap. I was trying to get a bit too clever with Zoom behind the scenes, and it spectacularly failed. So just talk to the key benefits of VPP participation for hospitals. There's three main themes. So it's about achieving a new standard of emergency preparation for the hospital, which we'll talk to further, creating a new revenue stream for the hospital, particularly for the engineering department, who isn't usually a source of revenue generation, and the community and sustainability benefits, helping facilitate that transition to renewables. So we've taken this table from a recent white paper that we developed with some generator manufacturers and contractors. And we looked at, I guess, the difference between common testing arrangements for backup generators. So in the three columns, we've got load bank testing, black start testing, and VPP participation. And we asked some key questions about to discern the difference between each of these testing arrangements in terms of emergency preparation. So first question, does testing encompass all the actions the backup system will need to take during a power emergency? So load bank testing, does it test the entire backup system from end to end? Load bank testing doesn't, or does it transfer the right loads onto the backup generators? Whereas black start testing and VPP participation, they both do, so they tick the box. Does testing simulate an actual power, or does testing simulate conditions that you would see under an actual power emergency, which is typically high loads in the hospital, high demand, because typically with heat waves and hospital air conditioning is a large proportion of total demand, and the time when these grid failures are actually most likely to occur, i.e., during business hours, but tending towards that late evening time. Some testing arrangements might test outside of after hours or on weekends, but typically that's not when a grid failure is most likely to occur. So VPP participation ticks the box for both of those elements to really simulate the conditions when a power emergency occurs. And does testing require the right performance that's needed during a real emergency event? So load bank testing, no for any of those. Black start testing, yes for fuel availability and fuel supply and quality. But in terms of speed of response needed, supporting required loads, testing exhaust systems, and critically in terms of staff emergency readiness and ability to respond to these emergency events, it actually undertaking a number of events during these emergency conditions when the grid most needs this service, it can help the hospital staff to understand what takes place and what happens, and they can get more a better understanding of the emergency sequence of events, if there is any needed during that event. So we've just got a quote from one of our participating partners at Chuka Regional Health. I'll read it through. The reality is that if the grid fails, it's probably going to fail on a stinking hot day in summer, right when you don't want it to. So I think VPP participation gives us the strength of conviction to say, well, we know that on a bad day, a high load day, and a high temperature day, that our generators are up to the job. So, Mark, I know if you're still on the line, it probably sounds familiar, given that it's come from your office. Is there any chance you'd be able to just elaborate a little bit further on your experience with this type of program, and in regards to achieving this new standard of preparation for the site?
Well, what a wonderful segue, and my apologies for not muting my microphone earlier.
We're 1-1.
The reason my phone rang was we are currently responding to an FCAS event, and both of our generators have just started. So we are right as we speak. Our generators are running. We've gone off the normal grid, as have probably many other businesses, and for those that haven't, you can thank us later, because we're providing the stability for everyone else. So I guess what more perfect timing you can have than that. We
did not set that up.
No, we don't control the grid. We like to think we do, but we don't. And look, I know that there is evidence around where I know of people that have participated in programs and can put their hand on their heart and say, on a 43-degree day in summer, they're comfortable knowing that their gear is going to work and will work comfortably. We've all heard about hospitals that have run out of diesel fuel, which happened at a large major hospital in South Australia. So black start testing, maybe the dot in there perhaps should still have a maybe a cross perhaps. We know of other places where people who haven't normally run their generators for extended periods of time have done so and found that they've had failure events that were totally unforeseen, such as the building getting too hot, or the exhaust system causing problems with heat transfer into the building, which was unforeseen. So we've certainly found that, in talking to the people that participate in the program the same as we do, that knowing it's going to work when you want it to work is absolutely key. And what better time frame than COVID for this sort of conversation, because a lot of places have been told to not test some things because of COVID. I think that's probably means that our strength of conviction isn't there, that we know wholeheartedly that our emergency systems are actually working when we want them and as we want them, which is supposed to be, a 99 point, lots of nines after it, uptime capability. So we've certainly had a lot of benefits.
Yeah, thanks, Mark. Much appreciated. And I cannot believe there was an FCAS event during this presentation, which is very interesting. I'd be keen to see what that was a result of after this. So run through these pretty quickly. That we've touched on the new source of revenue. So hospitals are paid to be on standby, regardless of whether an event is actually a call. You could go through a whole summer and an event is not called. You'd still be paid, because you're paid for your ability to respond to that event rather than actually responding to the event. And then for any events that you do respond to, and you do switch over to generator power, you're reimbursed for those fuel and operational expenses. So it's the site is VPP participation is fine, so the site is not out of pocket in any way. And this new revenue stream, as many hospitals have already done, can be used to facilitate upgrades to backup power systems. Whether it be switching, replacement of controllers, monitoring systems, diesel fuel tanks, whatever it may be, in order to upgrade that backup system so the site is comfortable participating in this program or similar, then that could be arranged. So indication of revenue for a small size hospital, 50 to 100 beds, maybe looking at 20 to 50K per annum. Medium size, 50 to 150K, and then larger hospitals in the order of 150 up to and beyond 250K per annum. Quick quote here from another hospital participating program in Castlemaine, just talking to the financial return that is provided to the hospital and supporting the broader community. Also, I've mentioned, generators, when they're run for an event, a BPP event, it can actually replace a monthly routine test and save on fuel costs where they align. And then these financial benefits can be reinvested into other projects. Community and sustainability benefits. We've touched on how this facilitates the transition to renewables by providing this firming capacity. And it's the most cost-effective form of your capacity. The existing underutilized assets, which can be put to use to provide this service. Participation, will help to reduce the likelihood of an outage occurring in the first place. And in terms of those critical peaking events when wholesale electricity prices go through the roof, by responding, adding more capacity to the grid and taking the strain out of the grid and reducing those price peaks, that actually filters down, trickles into everybody's everybody's energy bills. So it's supporting the broader community in terms of energy costs. Rakesh, I'll hand over to you for hospital considerations.
Thanks, Stu. So yeah, as I said at the beginning, I'll be going through a bit more technical stuff here. And we've just actually had a question from Trevor Marshall asking about how this links with existing processes of solar power and participation in the critical peak days. So I assume, Trevor, that your hospital is in the AusNet network. It's a great question, and I will go into that now. So the first key consideration that hospitals will have is what type of on-site generation you actually have. So if you have solar, what we're referring to here in terms of flexibility is you get to choose what the asset does, right? So solar PV doesn't really fall into that category typically in terms of the amount of power it generates, because obviously you get to choose how big the array is when it goes in. But its efficiency and the amount of power it generates during any given time is very much driven by the elements. On the flip side, you've got your backup generators. Some of you have cogen, some of you have trigen, and some of you may even have batteries on site. Those types of assets are things that you can control more easily. So in general terms, the output of your generators is what gets measured, and that is what defines the benefits that you are providing to the grid, as well as to yourself, the benefits against which you are being paid. So in certain programs of ours, we put a meter on the output of the generator itself, and that is what gets measured during the event. So under the AS4777 guidelines, typically when backup generators run at sites where there is solar, the solar arrays have to be turned off, or at the very least ramped down. This means that you can maximize the output of your generator, and therefore you can get paid the maximal amount for that. And this is the type of thing that I would work with you on to make sure that we're maximizing the benefit you can get. If you're already participating in critical peak demand days, that's fine. You are allowed to do both. So there's no real impact on the activity that you're going through right now. It's what can be classed as a double up that you are allowed to do. So hopefully that covered the question, Trevor. But if you want to follow up with one, I'm happy to go into more detail later on. All right, cheers. So I'll just recap there. The first thing you would think about is what type of on-site generation do you have, and how flexible is it as viewed by the market? The second question I would ask is, how do you run and test your generators today? And is there anything about that you would like to change? So as I said earlier on, we look to mimic existing load transfer sequences wherever possible. So if there was to be an event today, as Mark pointed out, the load transfer sequence that he already had programmed in is the one that took effect. And he was providing, with his site and with their generators, they were providing SCAS benefits to the whole grid. So If you're happy for that to continue, then that is the method of response that we would continue to use as well for VPP participation. But on the flip side, if there's anything about it you would like to change, for example, you have open transition now, and you would like to have closed transition, then we can work to make that happen for you. We're going through that process with a couple of hospitals at the moment. They have open transition and they want closed transition switching. We are funding that process, and we are providing them with engineering support to interface with the distributor, so that in about, 3 to 6 months time, depending on how quickly the distributors move, as we all know, they don't necessarily work as fast as we would like them to. The site will have closed transition switching, and that is equipment they get to keep and use whenever they want for the rest of time. So that's a benefit to the site, which I'm sure we can agree is very good. The next question I would ask is, how much of your site load do you transfer over to backup power? Some of our customers transfer the whole site over to backup power. Other customers who don't have closed transition switching, for example, or they just don't want to run everything on generator, they choose to transfer individual boards on. So the likes of chillers, fans, things that are non-essential loads, they will transfer over one by one. That is fine as well. You just have to choose which of the two you would like, and then we will work with you to help you select loads to make sure that you are maximizing the benefit. The next consideration would be whether you want to respond automatically or manually. So originally I said that we will put equipment on site that provides a control signal to run your generators, but you don't have to use it. In the case of FCAS or frequency response, you don't have very much time to make the decision, so it has to be automated. But some of our programs have notice periods of about 10 minutes. If you are able to respond manually within 10 minutes, then of course you're allowed to go ahead and do that. For example, at Echuca, I know that there's an app on the mobile phone that you can pick up and just press a button, the generators transfer over. They're able to do that within 10 minutes, so that's just what they do, and you just have to decide how you want to respond. In terms of the equipment installation as well, that's the last bit. Most of our equipment gets installed in a non-intrusive way. We use split-core CTs so they can be installed on existing cables without having to isolate anything. We take voltage references from general lighting and power boards, which typically can be isolated without any problems. Every now and then, though, there may be a case where something needs to be done and something has to be isolated. In these cases, we will work with you to make sure that we work in with any existing sort of maintenance windows that you have scheduled, and we'll make sure that it happens in a very convenient way for you. So moving on, we'll talk a little bit about the common questions that we get as part of this. So I've broken it down into 3 categories here. The first main category is people are reluctant to use their generators, right? And there's this misconception that if you're using the generator for VPP participation, then it is not available for backup power purposes. And as I said previously, that is not the case. We tend to use existing load transfer sequences, and we do not override any logic that already exists. So if your generators are operating as part of a VPP, and let's say the power goes out during that event, you receive a signal to switch back to grid power at the end of the event. But if there is no grid to go back to, your existing control logic should stop you from switching back to grid power and keep the generator running. If you are switching over manually, then of course you can run that check yourself. And as I said at the beginning, there's nothing stopping you continuing to run on generator power, even if the event has ended. What happens if the generator isn't available? And I covered this earlier on as well. If we ask you to run and your generator doesn't work, that's fine. It's obviously far more important to you to fix the generator. And I would actually argue that it was better for you to find out in that way when you had the grid to go back to, rather than if there were to be an actual power outage and you try to run your generator and it didn't work. So participating in a VPP does provide that benefit. Of course, if you have scheduled downtime coming up, months into the future or weeks into the future, you can just let us know, and we will take note in that way. Does this result in wear and tear? We went through this earlier. There's about 30 hours worth of running per year, and most generators are able to run for tens of thousands of hours, which is the advice that we've received from multiple engine manufacturers. It's actually better for you to run your generator more often than is the case. At hospitals, of course, this isn't necessarily applicable because you tend to have some pretty good testing procedures. So you should understand more than anyone, really, that running your generators for an additional 30 hours a year probably isn't going to lead to major problems. And of course, the fuel that you use through running in a VPP will be paid for by us as well. And then moving on, is there any impact on the existing mains failure logic? The answer is no. We make use of any logic that you already have, and that always takes precedence. So your ATS, if there were to be a mains failure, will still carry out the exact same functions as before. And the last common question we receive is about external control. The devices that make the decisions to send the signal to your load transfer switch, they are all installed locally. And you always have that override capability if you do not want to respond. So I'm sorry I rattled through that a little bit quickly because we are running short on time, but I'm hoping that that covers the types of questions that may have been going through some of your heads as we were speaking. Back to you, Stu.
Thanks, Rakesh. So just looking towards the coming summer period, I know, Mark, we were discussing earlier what the outlook is on, I guess, the situation coming this summer with COVID and somewhat suppressed demand, cheaper power prices. I guess we don't have a crystal ball, but certainly the grid is in a vulnerable position, and during the summer months, there's certainly increased stress from extreme weather, climatic events, and it's when these resources are needed the most. So the summer is really the critical period, and it's also the critical period when there's an increased risk or chance of a grid disruption, and therefore hospitals are needing to run on their backup generation systems. So it's actually when you need to have complete confidence that your backup system is going to perform as intended. And it's also the period when the most revenue is earned from this program, because it's when the grid really needs this service. We spoke about the critical peaking program, and then the frequency response program and emergency grid support. So critical peaking and emergency grid support are most relevant during the summer period, whereas the frequency response program is year round. These events can occur for these under frequency events can occur all year round, whereas critical peaking is most likely during the summer period. So what we're working with a number of hospitals now to ensure that they're enabled, technically enabled and enrolled into the VPP before the start of the critical summer period. So now really is the time. It can take up to 3, sometimes 4 months to technically integrate a site into the VPP from a communications and market compliance standpoint. Metering and the like. So if there was interest in ensuring enhance this level of emergency preparedness and start this this new revenue stream, now is really the time to seriously consider it. So Enel, we work with over 200 businesses across Australia who participate in our virtual power plant, or all sorts of different types of customers. So we'll leave it there, and we might just roll into a bit of a Q&A session. Just check if we've got any further questions. I know, Rakesh, you picked up a couple during the session. Doesn't look as though we do.
So Stuart,
just a very quick one.
If you'd like to flick back to the screen where your contact details are, anyone that wishes to send you an email can choose to do so. Fantastic. And what I'll do is if people have a question and if they want to put their hand up, I can actually put their voice through and they can ask you directly rather than typing. All right, I'll do that.
Fantastic.
Okay.
And also, I know, just to clarify, Mark, you mentioned that there was an FCAS event that Echuca responded to during this presentation. So just to clarify if we didn't mention it before, but FCAS stands for Frequency Control Ancillary Services. It's a market in the wholesale. It's called an ancillary services market in the wholesale electricity market. I won't go into too much detail, but it's basically what we call frequency response as the program, but the formal name for the market is called FCAS.
Steve's got a
question. Just very quickly on that. Sorry, before we jump in there, sorry guys, I promised to find out. It was the AGL Baker Inlet Power Station in Adelaide on Torrens Island, just near Adelaide, sorry. About a 210 megawatt power station that tripped suddenly, and the frequency looks to have gone down below 49.7 hertz, which is not insignificant, if anyone was curious.
Thanks, mate.
Fire away, Steve.
Thanks, mate. Thanks, Stuart, for pardon me, a great presentation. As you know, we're already participating in the demand response, which is working really well for us, and we do it for a selected load, which is just our chillers. So we just, under high demand periods, we change our chillers onto generators and contribute to the grid in that manner. But one thing that went really well for us was having the equipment installed by NLX and the process of having that installed and the quality of the installation. And I thought it might be worthwhile just going over the process of installing that equipment, Stuart, and what sort of space it takes up, and the amount of infrastructure, just to maybe answer any concerns from people considering going ahead with this.
Yeah, thanks, Steve. Mate, great question. I might actually give this one to Rakesh, because this is his specialty in technically integrating sites. Can probably provide a bit more detail than I can.
Yeah, sure. So thank you, Steve. In terms of the equipment, most of the equipment that we put in is panel mounted, it's bin rail mount, similar to the typical power analyzers that you would see as part of any normal site. So it is quite small. It's kind of like, little box equipment that we would put in. That would be the main side, the grid side equipment that we would put in to measure consumption on the site and deliver the signal. Other equipment that goes in is like utility metering. So your utility meter that you have at your site now, against which you get billed, that is what gets installed on the generator circuit. So it's not very big. There's a standard NEM compliant meter that would go on a meter panel, either indoors or outdoors, depending on where your generator is. And then in terms of the, sorry, Steve, just one clarification. Were you wanting to know about equipment that goes in as part of closed transition switching as well?
Yes, please, Rakesh.
Yeah, okay. So this is a little bit more involved, as those of you who have got it will probably know. Typically, we constrain it to the following. So there will be a new controller on the generator with synchronizing capability and export capability where required. There may have to be a new 4-pole isolator put in on your generating circuit in line with an update to AS3000 from 2018. But that is to improve the safety and reliability of your generating circuit. That can be quite large, depending on the size of your generator. 2000 amp 4-pole breaker is not small. And then there's protection relays as well, which have all of the necessary ANSI code protections, overcurrent, undercurrent, rate of change of frequency, vector shift, neutral voltage displacement if you're a high voltage consumer. But these tend to be small relays, similar to your overcurrent protection, relays that you will typically have at your site already. We look to put these in the most convenient places, making use of existing switch room capability wherever possible. So depending on the degree to which you get involved and how much infrastructure needs to be put in, there can be a varying spectrum of space that's required.
And Rakesh, that equipment is all put in at the expense of NLX, isn't it?
That is correct, yes.
Yeah. And I must say, the equipment that was put in at our site, we're a new hospital, and I'm very fussy about the equipment that's installed here, and I was thrilled with the quality of the installation. I didn't have to pick it to pieces and go and get people to redo things, which was a nice surprise.
Pleased to hear that. Thank you. We'll pass that on to our contractors for sure.
And just to further clarify, the metering hardware and technical integration, yeah, we completely cover. In terms of the synchronization upgrade, which is a more extensive scope, that's when we look to utilize the revenue stream as a result of this program to facilitate and finance those upgrades. So it's a way of using our using the energy market and using the grid to finance critical infrastructure upgrades that may not have otherwise been obtainable without this opportunity.